So far, we know we can use the outcome around the cutoff, compare the outcome for the people who just above cutoff and the outcome for the people just below the cutoff, compare the difference in these two groups people's outcomes. That can give us the causal effect for the people around the cutoff. And the next question is how to estimate the outcomes difference around the cutoff. So that's the estimations problem. How to estimate the discontinuity around the cutoff. So how to estimate this discontinuity. So there are two types of strategy to get this discontinuity estimate around the cutoff. One is so-called parametrics or global method. And in this method, we will use all available observations, but we need to assume specific functional form for the outcome and their assignment variable, their relationship. We need to have the correct functional form for the outcome variable and the relationship between the outcome variable and assignment variable. And based on this functional assumption, we can be able to estimate correct discontinuity at cutoff. So why we need to do that is I use this example to demonstrate why the functional form assumption for the outcome and the assignment variable is very important. So in this example, the y-axis is the outcome. And horizontal axis is your assignment variable. That's typically we use the x to represent. And here is the cutoff. So above cutoff you get a treatment, below the cutoff you do not get a treatment. Okay. And so in this example you can see, in fact the data tell you actually there's no discontinuity around the cutoff. You can see the data point actually go very smoothly over the cutoff. But suppose you assume the relationship between the outcome and assignment variable is linear. For example, in the data below the cutoff, you use the linear function to estimate, to fit the data. And for the data point above the cutoff, you use another linear function to fit it. And you want to compare these two linear functions, their estimate at cutoff. So their intercept at cutoff. So in that case, if you assume the assignment variable and outcome variable, their relationship is all linear, you will get very large discontinuity estimate. But actually, this is not the truth, because the truth is the assignment variable and outcome variable relationship, they have some nonlinear term, nonlinear. So this nonlinear relationship, if you do not really use the right functional form to capture the relationship between the outcome and assignment variable, you will misspecify and make you have the wrong estimate for the discontinuity at cutoff. Okay, so if, for example, if you use the second order or third order polynomial term, then you might be able to capture this nonlinear relationship. Then you might find there's no discontinuity here. So in this approach, you need to have the right functional form to capture the relationship between the outcome and your x, your assignment variable, Okay. So so here we will try to estimate or try to model the potential outcome of potential outcome. It's determined by some smooth function f of x. So for example, y0 is determined by the constant term, the intercept, and the f of x, some functional form x. some functional form for the assignment variable. And y1 is just y0 plus the causal effect, plus the treatment effect. So we want to estimate the rho. So we will run the following regression. The y is the outcome, and the key things is after we control the relationship between the x and y, the outcome and assignment variable, we want to focus on the treatment variable, its coefficient. This coefficient is captured the discontinuity estimate at cutoff. Okay, and also in the previous slide, we say this discontinuity, that means the difference between the outcome for the people who just above cutoff and the outcome for the people who just below the cutoff, their difference, these two group of people, their outcomes difference can help us to identify the causal effect around the cutoff. So this rho this is the key thing we want to estimate. So typically we might use some flexible polynomial regression to estimate. Or for example, the function model p order, f of p, the p orders polynomial term. So usually we might not use a lot of polynomial term, maybe just second order or third order. That might be enough. But we need to use some flexible polynomial functional form to estimate the relationship between the assignment variable and outcome. And we usually will allow the assignment variable, their relationship are differ on both sides of the threshold at the cutoff. So that means the relationship between the account and assignment variable, they can be different, have very different relationships before and after the cutoff. So that means we usually will interact our assignment variable and the treatment variable. Because treatment variable, this will be equal to 1 means is above the cutoff. And if 0 means below the cutoff. Okay. The assignment variable is below the cutoff. So that can help you to give you very different relationship for the outcome and assignment variable before and after the cutoff. Okay. So that means we allow on each side the f of function could be different. And usually we does not directly use the x as our covariates as our regressor. We usually will change the x to recenter our x to the cutoff. So usually with our regressor actually is x delta. So this step will ensure the treatment effect at cutoff can directly represented by the coefficient on the treatment dummy. Okay. Because all other terms at cutoff when x is equal to c these terms are all become 0. And then the coefficient on the treatment variable will directly represent the discontinuity estimate in the outcome at cutoff. Yeah, so later we will show that. So usually our regressor for assignment variable actually will be defined like this: minus cutoff, x minus cutoff. So we usually estimate the following regression. The outcome, and we focus on the coefficient on the treatment variable, and we control a lot of polynomial term, and we also allow the x relationship could be different before and after the cutoff. That is, if this is before the cutoff, the x and outcomes ratio is beta 1. But after the cutoff, it's become beta 1 plus beta 1 star, something like this. So we allow different relationship for the assignment variable and outcome before and after the cutoff. And we also recenter our assignment variable to the cutoff itself. So our regressor actually is x delta. So that has very important benefit because usually we want to estimate the causal effect at cutoff. So in that case, we want to estimate when x is equal to c. So if that, this all term will become 0 when we want to estimate the c. And the only difference at the cutoff is happen at c. We compare the intercept here. So this intercept is alpha plus rho. This intercept is alpha. So the discontinuity can represent by the rho, this coefficient, this rho coefficient. So in our example, we will estimate the following regression using the cubic term. So usually, so we run the mortality, whether you die or not, and based on what your age, and you usually will minus the cutoff, so that means minus 21, and we use third polynomial term, and interact with the x. That's typical case we will do, and we want to focus on the rho. So rho can capture the discontinuity in the mortality rate at the 21st years old. And that can represent, based on our previous slide, previous lecture, it can represent the effect of the legal access to alcohol on mortality rate at 21st years old. So here's the result. So here we just focus on the dummy, the coefficient on the dummy for the age above 21st years old. And the first panel is represent the estimate for the deaths due to all the cause. And you can find the discontinuity estimate is positive. That means above the 21st birthday, the mortality rate will increase by around 9.6 percentage points. So it's quite large. And they use different functional form, either quadratic or cubic. They actually give very similar result. And further, they try to know is this is due to external cause or internal cause. So external cause means they die due to some accident, car accident, traffic. So that's external cause. And internal cause is due to the cancer or some disease. And they find the result actually are all generated by the external cause. And for the internal cause, actually the estimate is not very significant. And that can also be found in the graph. So the graphs, the first line shows all the cause, and this is external cause, and this is internal cause. And you can see their discontinuity for all cause actually happen at 21st years old. Right after 21st birthday, the mortality rate, the death per 100,000 person started to drop from around like 90 to the 100, something like this. And that's all driven by the external cause rather than internal cause. So the internal cause basically no discontinuity at the cutoff. That's also consistent with our estimate, their estimates. Okay, so these actually give you very strong evidence suggest drinking alcohol might make you die, and that's for the young people. Basically, it's due to the external cause. And you can see actually these estimate the mechanism they adjust is by is due to the external cost, actually cannot really apply to the old people. So the causal effect they get using this RDD design is just for the people around the cutoff, around 21st birthday, or for the young people. For the old people, might not their estimate might not be applied. Okay. So the next question is how we determine the functional form for the assignment variable and outcome. How to determine the polynomial order. So there are two approaches. One is so-called F-test approach, another called AIC approach. But F-test approach, in the literature, people seldom use that. So I just leave this for your own reading. I only focus on the AIC approach. Most people use AIC approach to choose the number of polynomial terms. Okay. So AIC approach, I think you might learn this criteria, statistic criteria from the statistics course. That's the criteria can help you to choose the model, your model, statistical model. And this basically is try to describe the trade-off between the goodness fit of the model and simplicity of the model. So the goal of the regression model is we try to use the few variable, try to feed the data better. So the goal is this. So the AIC criteria actually is try to mention these two trade-off. So the AIC's formula is consisted by these three terms. One is the number of the sample. Another is sigma b squared. This is the residual variance. And you can consider this term if you include more regressor, basically more polynomial term, you will capture more variation. So the residual variance will go down if you include more regressor, more polynomial term. But AIC criteria also have the penalty here. It's P. It's the number of the parameter you need to estimate. So if you include more regressor, more polynomial term, you need to estimate more coefficient. So this term will be increased if you include more regressor. So the best model is you choose the model that gives you smallest AIC, smallest value of AIC. And that's the best model. That means you can keep the residual variance very small, but also you don't have very big model, regressor. A lot of regressor you need to choose. So in the practice, usually you can use linear to control the relationship between assignment variable and your outcome. And that will give you one AIC1. And if you use second order polynomial term, you get another AIC value. And if you use third order, more regressor, you get AIC3. And you just pick the smallest one. For example, AIC3 is the smallest value. That you can use that to justify why you use this model regression discontinuity estimate as your main result. Okay, so that's the polynomial approach, a parametric approach. And second approach is so-called the non-parametrics or local method. And these methods, we will just use the observation around the cutoff. And we want to compare the outcome for the people who get treatment and who do not get treatment within specific bandwidth. So that is, we need to decide what do you mean by the around the cutoff. So how close is around the cutoff? and that will determine by the bandwidth choice. So bandwidth is, you can consider the interval. So how close is mean close. Okay. So the key question for the non-parametric method is choose bandwidth. To choose what's the specific interval you need to go to the estimation around the cutoff. Okay. So the non-parametric approach does not specify any particular functional form of the outcome and assignment variable. Instead, we just use the data within a small neighborhood, and sometimes we call it's called the bandwidth, to estimate the discontinuity in outcome at the cutoff. So basically, we compare the average outcome just above cutoff or just below the cutoff. The difference. And these methods it's good, but might give you some bias. And further, people will also use so-called local linear regression to further reduce the bias. So what's the bias we might generate is due to the trade-off when we choose the bandwidth. Okay. So here I just give you one example. So in this example, the y-axis is the outcome and the horizon axis is the assignment variable. And here is the cutoff. And from the graph, there's no discontinuity, you can see. And the edge is the bandwidth. So for non-parametric approach, we just use the data around the cutoff, just use the data here and data here. And the first approach is just suggest we just take the average of the outcome around this area, this interval, and this interval. Okay. So if you do that, you will get the estimate. For example, average here is A, can represent average outcome is A, and here average outcome is B for the outcome above the cutoff. So the estimates you get for this is compare A and B. So you get very large discontinuity. But actually, at cutoff, there's no discontinuity. And this is because you have too large bandwidth. So if you can reduce your bandwidth to here, the H1, smaller bandwidth, that will give you better estimation, for example, here. And then the average will become this. So the bandwidth estimate will become smaller. But there's a trade-off. If you use small bandwidth, you may not have enough sample size around the cutoff. Or even you don't have any sample, any individual, just around the cutoff. So you will get unprecise estimates if you shrink your bandwidth. But shrink the bandwidth will also give you better estimate for this discontinuity. That's just this example can show that. If you shrink your bandwidth, you will more close to the truth. The truth is no discontinuity at cutoff. Okay. So, but if you use the non-parametric approach, typically we'll use is so-called local linear regression. And here, the linear regression does not mean you assume the functional form between the outcome and assignment variable is linear. It's just they do the Taylor expansion around the cutoff, at cutoff, and do another Taylor expansion around the cutoff. And we want to use this Taylor expansion, try to compare their estimate at the cutoff. Okay. So, and these tail expansions, the formula will become like this linear regression, linear term. So you basically is equivalent. You run the linear regression within a window, within the bandwidth around the cutoff. Okay, so if you do that, the bias will become smaller even you use the same size of bandwidth. Given you use the same size of bandwidth, that will give you small estimate. So the new estimate for discontinuity is B plum, A plum. That will be better than the AB. So the discontinuity is smaller. And if you can use even small bandwidth, for example, that will give you better estimate. For example, here, even small bandwidth, you might get much better. So here you do some Taylor expansion here. That will give much more discontinuity. That's more close to the truth. No discontinuity at cutoff. But again, if you use just around the cutoff, the sample size might be very, very small. So your estimate for this estimate coefficient for the treatment variable, the discontinuity estimate might be imprecise. Okay. So the main challenge of the non-parametric approach is choose the bandwidth, and basically is essential have two trade-off between the bias and precision. So if you choose large bandwidth, you get more data points, and you might get you will get more precise estimate, treatment effect estimate. But you will use the data points very far from the cutoff, and that will make your treatment effect estimate, the discontinuity estimate, be biased if you choose too large bandwidth. Okay. So the key for this approach is how to choose the bandwidth. Okay. So for this alcohol example, we might choose the bandwidth is 180 days before and after the 21st birthday, and run this local linear regression. And we want to focus on the coefficient on the treatment dummy, and let's capture the discontinuity at cutoff. That is the two lines intersect at the cutoff, their difference. Okay, and we usually will present this estimate based on different choice of bandwidth. For example, 200 days, 300 days. And you will expect the result. This is the RD estimate at the 21st birthday. And you use different bandwidths, 0.1 years, 0.2 years, until 2 years before and after 21st birthday. And you will expect the results are quite stable. Maybe there's some noise, some variation. If you use very small bandwidth, that's typical case. So no one really care about if you use very small bandwidth, because you don't have enough sample. So the estimate will be biased, will be noise, not very precise. But at certain points, you need to quite stable. Does not change too much. Okay, so finally, how to choose the bandwidth? There are two approaches. One approach is so-called cross-validation procedure. That is to choose the bandwidth that can produce the best fit for the relationship between the outcome and a sample variable. You can use RSPE, the predict error, try to determine what's the best fit. So you try different bandwidths, 180 days, 200 days, 300 days, and you use the bandwidth that can give you the smallest predict error. That will be the best bandwidth. Another approach is not use the data. It's based on the formula, the so-called plug-in procedure. That is, some econometrician, statistician, they based on the the formula, because the bandwidth is trying to balance the bias and precision. So there's the optimal. So you can derive the optimal bandwidth, try to balance these two things in terms of try to minimize the mean square error. And they derive some formula. And this formula, they need to plug in some parameter that can directly give you the optimal bandwidth, is the size. And you just need to plug in the formula. They require some parameter, and you plug in, you can directly give you the answer. The optimal bandwidth is maybe the 100 days for alcohol example. And there are several papers you can read. This and these two papers. One is from Review of Economic Studies, and this is the conventional paper. And you can look at it. And you can use the optimal bandwidth to justify your result. Maybe you use 0.9 years is the optimal bandwidth. You will use that as your main result. But you also need to show your result, actually your estimate is quite stable, does not really not very sensitive to the bandwidth choice. Okay. So that's for the RD design, how to estimate the discontinuity at the cutoff.